A little while ago, a subscriber asked me a brilliant question, one that gets right to the heart of the biggest, most persistent mysteries in all of biology. Why did life go through all the trouble of inventing sex? When just copying yourself, cloning, is so much faster and easier. It's a question that has baffled biologists for centuries because, on the surface, sex makes no sense. It's a paradox at the very foundation of our existence. And the honest answer is, it's a story that's over 1 billion years old. And untangling it is one of the hardest problems in evolutionary biology. But the clues we have point to an incredible story. It's a story about a planet in crisis, a relentless army of invisible enemies, and what might have been a tiny accidental glitch in cellular machinery that unlocked a whole new way of being. This is the story of how a simple mechanism for fixing broken DNA may have accidentally switched on evolution's turbo button and in doing so created the world we now know. From an engineering perspective, sex is a terrible design. It's inefficient, it's risky, and it's incredibly costly. Imagine you're a perfectly adapted organism thriving in your environment. The fastest, most effective way to pass on your winning set of genes is to just make a perfect copy of yourself, a clone. It's 100% efficient transfer of your genetic legacy. Now consider sexual reproduction. First, you have to find a partner, which takes time and energy, and often involves dangerous competition. Then you only pass on 50% of your own genes. You take your perfectly good genome and combine it with the genes of some other individual, whose genetic quality is a total gamble. And to make matters worse, half of the offspring your entire population produces, males, won't be able to produce any offspring themselves. Biologists call this the twofold cost of sex, and it's a massive evolutionary hurdle. So why would any species trade the simple factory of cloning for this bizarre and wasteful system? For evolution to select for a strategy that immediately cuts your reproductive output in half, the benefit can't just be minor. It has to be revolutionary. To find that benefit, we have to go back, way back, to a time before animals, before plants, to a quiet and dangerously uniform world. For the first couple of billion years, life on Earth was dominated by single-celled organisms like bacteria and archaea that reproduced by simple division. They copy their DNA and split in two, a process called binary fission. The offspring was a genetic replica of the parent. This was life's original strategy. If it ain't broke, don't fix it. And for a while it worked beautifully, allowing for explosive population growth. But this world of near-perfect copies had a hidden fatal flaw. While early microbes had ways of exchanging bits of DNA, a process called horizontal gene transfer, populations were still largely made of genetic stand-ins for one another. And two major evolutionary forces were lining up their sights. First was an invisible, relentless enemy: parasites. In a population of genetic lookalikes, if a virus evolves a way to infect one individual, it can infect them all. The entire population shares the same lock, and the parasite has just found the key. An epidemic wouldn't just be a disaster, it would be an extinction-level event. This constant arms race between host and parasite is known as the Red Queen hypothesis, named after a character in Through the Looking Glass, who has to run as fast as she can just to stay in the same place. For clones, standing still genetically was a death sentence, but even without an enemy, this world was at risk of rotting from within. This second problem is a concept known as Muller's ratchet. Every time a cell copies its DNA, there's a small chance of an error, a mutation. Most are harmless, but some are slightly bad. In an asexual organism, any harmful mutation is passed down to all of its descendants. It's permanent. Imagine a line of clones. One gets a bad mutation, all its kids have it. A few generations later, one of them gets another bad mutation. Now that the whole branch of the family has two, there's no way to go backward and create an offspring that is cleaner than the parent. The genetic ratchet clicks forward, accumulating more harmful mutations, dragging the entire species toward a slow, inevitable decline. Finally, there was a frustrating speed limit on innovation. What if a beneficial mutation appeared? Let's say in one clone, mutation A arises, and somewhere else in a separate clone, another great mutation, B, appears. In a world without sex, these two incredible advantages can never meet in the same descendant. The lineage with A and the lineage with B are now competitors. This clonal interference puts a severe brake on evolution. So this was the theoretical crisis facing early life. It was hunted by parasites, slowly decaying from genetic rust and unable to innovate quickly. Life needed a reset button. It needed to shuffle the deck. And it may have found one, not through some grand design, but through a fortunate accident. A system that was likely built for something else entirely. DNA repair. Sometime after about 2.4 billion years ago, our planet went through a radical transformation, the Great Oxidation Event. Photosynthetic bacteria began pumping a new highly reactive and toxic gas into the atmosphere, oxygen. This was a catastrophe for much of life, but some organisms evolved to use it, unlocking huge amounts of energy and paving the way for more complex cells, the eukaryotes. But this high-energy lifestyle came with a side effect: DNA damage. The very oxygen giving these cells life was also bombarding their genetic code. One of the most dangerous injuries is a double-strand break, where both spines of the DNA helix are severed. A single unrepaired break can be lethal. How do you fix it if the template itself is destroyed? You need a backup copy. Here's where one of the leading hypotheses for the origin of sex comes in. The idea is that the machinery for sexual reproduction evolved from the machinery for DNA repair. The thinking goes something like this. Some early cells developed the ability to fuse together, creating a temporary cell containing two full sets of chromosomes. This diploid cell now had exactly what it needed: a pristine backup copy of every gene. This set the stage for a process that would become meiosis. It likely started as an ancient DNA repair system. A cell would line up its broken chromosome with the undamaged one from its partner. Using the partner chromosome as a template, the cell's repair machinery could flawlessly patch the breaks. This process, called homologous recombination, was a game changer for keeping the genome intact. During this repair process, something magical happened. Sometimes the machinery would swap entire sections between the two chromosomes. This physical exchange of genetic material is called crossing over. After the shuffling, the cell had to get back to having only one set of chromosomes, so it divided twice, resulting in 4 new cells, each with a single, completely unique set of remixed chromosomes. This two-step dance, shuffling via crossing over, then dealing the cards through 2 divisions, is the core of meiosis. It likely started as a way to fix broken DNA, but its side effect, creating endless genetic variety, was about to change the course of evolution forever. It didn't just fix the code, it remixed it, creating combinations of traits that had never existed before. This was the key that may have unlocked evolution's turbo button. This new system, likely born from the need to fix DNA, was a devastating weapon against the problems that held asexual life in check. First, it was a powerful counter-strategy to the Red Queen's curse. The constant shuffling of genes meant that every single offspring was a new genetic experiment. To a parasite that had evolved a key for the parent's lock, it was a nightmare. The offspring had different locks. A sexually reproducing population is no longer a static target. It's a moving, shifting, endlessly creative one, providing a powerful firewall against disease. Second, it put the brakes on Muller's ratchet. That one-way street of accumulating bad mutations now had a U-turn. Because of recombination, it became possible for a parent with 5 bad mutations to produce an offspring with only 1 or 2 or even 0 by combining the clean parts of both parents' genomes. It allowed population to purge harmful mutations, stopping the slow slide toward extinction. But the most profound advantage was the solution to clonal interference. In the world of clones, if beneficial mutation A and B arose in different individuals, they were competitors. In the new world of sex, they could become collaborators. Through the magic of recombination, it was now possible to produce an offspring that carried both beneficial mutations. This changed everything. It meant evolution could now happen in parallel. Beneficial traits from different corners of a population could be brought together, creating super-adapted individuals. This is the idea behind the fission model, and it shows how sex can dramatically accelerate the pace of adaptation. Instead of waiting for the winning lottery tickets to show up one by one, sex allows a population to collect and combine them. Some experiments have even shown that sexual populations can adapt to new environments significantly faster than their asexual counterparts. This wasn't a small tweak, it was a fundamental shift in the speed of life. This transition happened somewhere deep in our ancestral line, likely in the last eukaryotic common ancestor, or LECA. Once sex was on the scene, it was so advantageous that it became a cornerstone of nearly all complex life. The first fossil that's widely interpreted as showing this new strategy comes from a rock formation in the Canadian Arctic, dated to about 1 to 1.2 billion years ago. Preserved there is a fossil of red alga called Bangiomorpha pubescens. What makes this tiny fossil so special is that it appears to show differentiated cell types that look like reproductive structures, perhaps even male and female gametes. It's considered the oldest known fossil evidence for an organism with sexual reproduction. This invention was a key ingredient for biological complexity. The genetic shuffling and rapid adaptation that sex provides are thought to be critical preconditions for the incredible diversity of life we see today. The world of clones was a world of repetition. The world of sex is a world of possibility. Every time two organisms reproduce, they perform a novel experiment, creating a unique biological idea. This ancient system for remixing genes is considered a major contributing factor to the Cambrian explosion, that spectacular burst of creativity around 540 million years ago, when most major animal body plans appeared. It's what allows a species to constantly evolve new ways to fight parasites, adapt to changing climates, and develop new features. It's a process found in almost all major eukaryotic groups: plants, animals, fungi, and protists, a testament to its importance. It's the reason why no two oak trees are the same, why no two tigers have the same stripes, and why no two humans, aside from identical twins, are genetically alike. The vast, beautiful, and sometimes terrifying tapestry of life on Earth is a direct consequence of this ancient evolutionary innovation. The simple need to patch up broken DNA in a newly oxygenated world may have accidentally created a system for generating near infinite variety. So, to go back to that brilliant question, why did life bother with the cost of sex when cloning is so much easier? The paradox isn't fully solved, but one of the strongest ideas is that life didn't invent sex for variety, it invented sex to survive. A leading hypothesis is that it evolved from a molecular toolkit for DNA repair, a way to fix catastrophic damage to the genome. But the side effect of that repair process, the constant shuffling of genes, turned out to be one of the most powerful evolutionary forces that the world had ever seen. It turned evolution into a collaborative process, allowing life to adapt and diversify at a speed that was previously unimaginable. The cost of sex is high, but the cost of not having it, stagnation, decay, and extinction, is likely far higher. Sex is the price life pays for its own complexity, its resilience, and its endlessly creative future. If you enjoyed unravelling this billion-year-old mystery, consider subscribing for more journeys into the deep past. And as always, thank you for watching, and I will see you in the next one. Bye for now.